Alrighty, welcome everybody. Today, for our webinar, we will be looking at really how cybersecurity is changing and really continuing to evolve alongside process safety. And so for the webinar today, we will be using the GoToWebinar application. And so as we start to go through the slides, if you're unable to hear, there's a question tool, and we have a number of staff on the line that can help you, get the audio enabled in all places and make sure that you're able to hear the webinar. You can also use that question tool to really ask any questions about the content as we go through the material today. And we should have about 10 or so minutes at the end of the webinar to really go through and answer those questions in depth. A little bit of background about myself. My name is Patrick O'Brien, and I'm a safety and cybersecurity engineer at Exida. My background is in chemical engineering, and so I started out really more on the process safety side, doing lots of process hazard analysis, some layer protection analysis, as well as some of the safety system design. And over time, we really started to see this change occur where cybersecurity was this new risk, and it really had a potential to impact process safety as well as having financial impacts. And so with that, I started to not just look at the process side of things, but also to really start evaluating cyber risks. And so now for my current role, I spend a lot of time looking at both the cyber and the safety side of things. One of the great projects that I had an opportunity to work on the cyber side was actually the exida book about implementing IEC 62443, where we tried to take a more of a practical approach that end users can look at and use when trying to implement cybersecurity for their systems. For exida as a whole, we really help our customers in three main areas. We were founded as a certification and assessment division, and so we started by working with manufacturers to provide certification to functional safety standards to really show that they were following a safe development life cycle. Over time, that's evolved to also include a number of cybersecurity standards as well as machine safety and automotive standards. Our next group is our lifecycle services, which is where I primarily am focused, and we really work directly with the end users, with the process plants to help them implement cybersecurity, safety, and alarm management solutions. And then lastly, we have a product or enterprise tools division where we have developed a number of lifecycle tools that really support the functional safety, cybersecurity, and alarm management activities that we use both internally and offer to our customers as well. Jumping into really the content of our webinar today, we'll focus in on three main areas. The first is the current landscapes for process safety and cybersecurity, understanding really where they got their roots and where they are today and what's continuing to change from a landscape standpoint. From there, we'll look at really how does cybersecurity challenge traditional process safety approaches, and what are some of the new concerns, new scenarios that this introduces. And then lastly, we'll look at what are some of the actionable steps that sites can take to really begin to address these risks and make sure that they don't have unmitigated risk from a safety or cyber standpoint. And so to dive into our current landscapes, let's first take a look at process safety. Now, really, when we talk about process safety, we're looking at the prevention of fires, explosions, and unintentional release for hazardous materials at chemical process sites. And so, a lot of the common activities that we would think of include process safety management, so the procedures for going through the design and taking the steps to make sure that safety is maintained over time. In terms of the analysis that's typically done, the major ones would be our process hazard analysis, or a HAZOP. and our layer of protection analysis, or LOPA. And really what we're doing here is evaluating all of the potential risks associated with our control system with human error that can lead to deviations in the process, and making sure that we have enough independent protection layers to mitigate our risk. We can also think about quantitative risk analysis, and this is sometimes done to really try to understand high consequence severity scenarios better, where we can really break down and understand for each of the steps that happens, what is the probability of that, and really do some more detailed modeling from that perspective. For those of us with a little bit more of a background in functional safety versus process safety, we can really think of process safety as an extension, or really something that has a lot of overlap with the analysis phase of the functional safety lifecycle, where we try to understand what are the risks to the system. And then for the rest of the functional safety lifecycle, there's a little bit more of a focus on actually designing and creating reliable safety instrumented functions. But process safety and functional safety really go hand in hand on the safety side of things. If we look back to really where was process safety started, there have definitely been government efforts and a lot of things that have been done to try to improve worker safety over the years. But really, when we talk about modern process safety, its roots go back to the 1980s. There were a number of really high-profile major industrial incidents that really had a major increase in awareness for the general public of the hazards associated with process sites. And really the picture or the main event that would be looked at is the incident in Bhopal, India, where a release of toxic gases resulted in over 2,000 fatalities. And so this was something that really kind of shook the world and was one of those first major incidents where we knew we had to do better from a process safety standpoint. And so from the 1980s to the 1990s, there now was a major push for more stringent regulations across the globe, both in Europe and the US, as well as other nations. And so we started to see many new directives coming out from the EU Occupation Safety and Health Framework, OSHA PSM, which is really what's looked at when we talk about process safety in the US. That was first released in the 1990s, and an updated version of the Seveso directive also came out in the 90s to really try to improve on and expand the original requirements. And so then if we look at from the 2000s to today, the regulations have continued to evolve, and we've also seen a number of different initiatives or different methods for implementing process safety. We've looked at it as part of overall quality management, and so really putting quality systems to not only improve our availability and uptime, as well as the quality of the products created, but also to use that as a way of improving the overall safety. We've seen a lot of work on specific process safety management, so putting the necessary policies and procedures in place to really maintain that safety, to have that company culture of safety, which we've seen time and time again, is really critical for avoiding these major incidents. We've also seen movement towards a continuous improvement approach where we use improved data keeping and metrics to really have better visibility into our systems and understand what steps we need to continue to take to make them safer. And then another continuing trend in process safety is what's been developed by the Center for Chemical Process Safety as a risk-based process safety framework, where we really look at how our risk changes with our different activities to have that continual risk-based focus for mitigating the likelihood of these cybersecurity incidents. And so we've really seen that from the 80s, we've had significant growth and changes in process safety. On the flip side, if we look at automation cybersecurity, here what we're focused on is preventing intentional or unintentional interference with the proper operation of automation systems. So thinking about things from industrial control, discrete manufacturing, the industrial Internet of Things or Industry 4.0. And so really we're preventing interference with these through the use of computer networks, operating systems, applications, or other programmable or configurable components of the system. Now, automation cybersecurity really does have many different names, from SATA security to PCN security. What I will most often use to talk about it is really this idea of the Industrial Automated Control System, or IACS. And so when we look at cybersecurity for these, connected in the physical world systems, we can try to, think about how things have changed over the years. If we go back to that starting point in the 1980s, cybersecurity really wasn't even a question for these systems yet. People were maybe asking, who would possibly want to hack into an automated system? If we fast forward to the 1990s, now all of these control systems really got this idea and this trend to now move towards a more interconnected and really Windows-based platform, which had a lot of benefits, but also we'll see has really opened them up to a number of cybersecurity threats as well. It isn't until really the early 2000s when we begin to really discuss and think about cybersecurity for these automation systems, but it's still more of an academic exercise. There may be some proof of concepts, but it's not seen as a credible threat. It wasn't until getting closer to the 2010s, the last decade, where with Stuxnet and a number of other higher profile attacks, that this was now something where we were really seeing an issue. And so in that, this last decade, we've seen a lot of development in terms of cybersecurity standards, both for specific industries as well as for some overall broader frameworks. And so really what we'll look at later when we think about how to integrate both cybersecurity and safety together, will really pull from the IEC 62443 standard. If we fast forward and look at cybersecurity today and think about what impacts it has on process safety, there are a couple of really critical statistics that we need to ground ourselves in to understand really how much of an impact cybersecurity can have. For a recent industry survey in 2019, it showed that just around 60% of industrial control systems had experienced an attack in the last year. And so this is, more than half of the control systems are seeing cybersecurity activity and potential threats. Also, as we think about, the growing trends of remote access, around 70% of industrial control systems now require some type of remote access, whether it is the process engineers checking in and seeing how the system is working, or the controls engineers, as well as thinking about contractors or suppliers who have third-party access to monitor the system. Now it's the vast majority of control systems are seeing this remote access. And with that, we can think about the amount of really internet-facing vulnerabilities and potential exposure there. And so from January to March of this year, the amount of remote desktop protocol ports used for remote access that are facing the internet jumped 50% as we started to move to more of a work from home setup during the COVID-19 pandemic. And so this jump, as well as all of the vulnerabilities that exist for remote desktops and a lot of times poorly utilized safety features, we really are at a time of really high exposure for cybersecurity. and it's higher than really what we've seen before. And so in addition to really looking at the landscape, there are two specific attacks from the last few years that I want to look at. The first one is going to look at the financial impacts that many people are familiar with cyber attacks having, but really to look at the scale and the level of exposure for industrial systems. The next case study is going to drive home a point that people may be less familiar with, but that's that cyber attacks also can create hazard scenarios for safety. And really, we're getting close to a tipping point where this is going to become a major concern. So for our first case study, we're going to look at the NotPetya cyber attack. This was, originally a targeted attack for one organization in the Ukraine, where it started with the Linkos group. They had an update server that was compromised. From there, though, the attack rapidly spread across the globe and really had a major impact on industrial companies on every continent. At first, the NotPetya attack was believed to be ransomware, but it was later discovered that the information on the infected machines was actually already deleted, and so there was no chance of recovering it. The attack was self-replicating in nature, and it leveraged two critical exploits, one being the Windows Eternal Blue and the other being Mimikatz, that allowed it with the Eternal Blue vulnerability to infect unpatched systems. So there were known vulnerabilities and known exploits that the attack used in order to get onto the system. But what made it so widespreading was that once it got a foothold on the system, it used a Mimikatz to actually steal passwords and was able to then automatically go onto patch systems as well. And so with that, it really was a rapid spreading attack. And we saw an impact for companies in many different industries. If we look at the cost of NotPetya and some of the major companies impacted, Merck, the pharmaceutical company, the estimated cost of the attack was $870 million. We also saw it for delivery, construction, shipping, food and beverage, and consumer goods. All major companies hit for over $100 million in damages. And the total cost of the NotPetya attack, looking at the companies who are most affected, as well as all of the other companies that had less significant impacts, the total damage for that one attack is estimated at $10 billion. And so we saw that what was originally a target attack of one company quickly spread and had a major impact on many other industrial sites as well. The second attack that we're going to look at is one that happened at the Sadara Petrochemical facility. This attack occurred in August of 2017, and it was named the Triton attack. Now, what is different about this attack and what is so important is that it wasn't just going after downtime or a financial loss for the system. It was actually designed to trigger a deadly explosion in the plant. Looking back, going through the analysis of the attack, researchers saw that the attack had successfully compromised the basic process control system. So the attackers had the ability to alter set points, to actually manipulate the physical valves and process out in the field remotely. They also saw that the attackers were attempting to compromise the safety system as well, which would give them the ability to not only initiate an unsafe state, but actually disable the safety systems that were designed to prevent the consequence, to prevent the explosion. It was later found that on the redundant safety system, that they only executed the exploit on one of the safety controllers. And so when the safety controllers were doing an internal comparison, they saw that they weren't running the same configuration, the same code, and so that led to a process shutdown. But this was really that one mistake in the attack for only targeting one of the safety controllers. That was the only step preventing this from being a major safety incident. And so it also had a couple of other key takeaways. The first was that the attackers were able to overcome a physical lock and key system so that they could update the controller remotely. And what this is so important to recognize is that for cybersecurity, there's really no 100% secure option. Even with something that at the time we believe is as secure as it can be, we still can see that attackers are continually attempting to compromise these systems, and given enough time, given enough resources, it's not a question of if an attack is going to occur, but really when and what layers are going to be defeated. And it also really provided a roadmap for future attacks targeting safety systems. It outlined, these are the steps to do when you're really trying to cause a safety consequence. If we think about what this means for cybersecurity and risk, we really need to understand that cybersecurity can affect multiple risk receptors. So with the Sadara Petrochemical facility, it could impact personnel safety. Also, if we think about altering the quality systems of a chemical site, it could also impact the product safety. And so for consumer goods or pharmaceuticals, that could have a major impact on the consumer. For environmental, we've seen attacks that have actually caused releases into the environment and have had major environmental impact. We can think about all of the financial impacts from lost production to equipment damage. There was actually an attack in 2014 where a blast furnace couldn't shut down and caused major equipment damage. And this, again, luckily, the local personnel were able to evacuate from the affected area. But if they weren't aware of the incident occurring, this was another one that could have had major safety impacts. And we can also think of some of the, say, harder to quantify impacts of cyber attacks, such as the loss of sensitive information and the impact that that has on company image. And so when we think about both safety and cybersecurity, it really comes down to managing risk. And this isn't something that, really companies have a choice to choose whether or not they want to. They're actually driven by a number of different factors and obligations, both moral, financial, and legal, to provide a safe work environment and really make sure that these types of negative incidents are mitigated to an appropriate level. And so to do this, to help guide this activity of risk management, there have been a number of regulations, as we looked at, for the process safety industry, as well as industry standards that really provide guidelines. And so often what's pointed to in the US and other countries as well, to really show adherence to the requirement of OSHA PSM or other regulations, is really the IEC 61511 standard. And so this outlines the functional safety life cycle, everything from the traditional process safety activities of risk assessment through the design of the safety instrumented systems to provide those layers of protection. It is a performance-based standard, so it doesn't tell users exactly what they have to do to achieve safety, but really gives them a life cycle and a repeatable step of activities that they can follow in order to achieve their goals for safety. Now, something new in this standard that came out in 2016 is it now points to security risk assessment for the safety system and all connected systems. So for organizations who claim to be compliant with the 61511 standard, there is now an obligation to complete cybersecurity risk assessment as well. And for this cybersecurity activity, we will point to and look at the IEC 62443 lifecycle that really follows the same approach of the safety standard in that it looks at the assessment phase, the implementation phase, and the maintenance phase. And so when we think about the new impact of cybersecurity on process safety, we really want to understand what are the challenges now that are being posed to process safety and those traditional activities. We can start by looking at what are some of the core process safety concepts. We can think about what are hazards caused by. We know that a hazard exists. There's the potential for harm because of the chemicals in use, because of the processes that are being conducted. But we're really looking at how can control failures, mechanical failures, or human error really lead to that unintended release, or those scenarios where we now deviate from our typical process. To protect against these hazards, to reduce our risk, we look at independent layers of protection that we're really able to stack. We can think about the Swiss cheese model, where as long as we have independent layers, we can continually reduce the likelihood that the ultimate event is going to occur. We also have relatively high maturity of industry databases that give us detailed information on our initiating events and the probability of failures of our protection layers, which really makes a more quantitative analysis possible. If we think about our typical layers of protection, moving from prevention to mitigation, we can think about having alarms and an operator process shutdown before we get to an emergency scenario. We can think about our automated safety systems that will shut the system down before we get to an excessive pressure. We can think about relief valves or rupture discs, where if our automated system is not successful, we're able to relieve pressure before we get to our rupture. And we also have mitigative controls, where once we've had the event occur, there are things that we can do to limit the severity, such as having passive protection layers with dikes, where we're limiting the release, or emergency response to try to, once the event occurs, really limit the harm to people. And so if we take this approach, if we think about a typical process unit, we could look at, say, an isomerization unit. The process really doesn't matter, but what does matter is for each of these chemical processes, based on the pressure, based on the chemicals used, there are the potential for hazards. And when we have releases, we can talk about the potential negative impacts. And so for our example, we're going to focus in on the isomerization reactor and really think about what impact would excessive pressure have here. If we think back to the Sadara Petrochemical facility, this may very well have been the unit in the refinery that was targeted to trigger that explosion. And so this isn't a far-fetched scenario in terms of both the safety and cybersecurity impacts. When we look at the traditional LOPA scenario, we can think about the cause being a control failure for the pressure control system. We have a good understanding of the failure rates, and so for BPCSs, we could look at that event occurring once in 10 years. In terms of protection layers, we can have an independent pressure transmitter with an operator response to shut the system down. We could have a high pressure safety function. Here we're looking at a SIL2 protection that is going to further reduce our risk. And then lastly, we could think about a pressure relief valve, where if the alarm response fails, if the safety system fails, we're still able to vent that pressure before getting to a rupture. And so looking at these traditional layers of protection, we're able to meet our target frequency, our tolerable risk for having this potential explosion. If we now switch to the cybersecurity side of things and think about the core concepts at the foundation of cybersecurity, now our cyber hazards are being caused not unintentionally by some sort of random failure or human error, but they're actually being driven by threat agents and attackers who are intending to cause harm to the system, who have a desire to create the worst case scenario. Now, we can also look at the impact of human errors for cybersecurity as well, in terms of introducing malware or providing an entry point to attackers. But really the core difference here is that instead of those random equipment failures, we're looking at an intentional adversary, someone who is going in and attempting to cause harm. And so with that, we also see that our assumptions of independence really now struggle to stand up to that. Because the attacker is able to bypass multiple protections, that cyber attack can really be a common cause failure of multiple layers. What we're also seeing is that industry databases don't have the detailed information, they don't have the level of research and tracking that we do on the safety side. And so for the threats and the effectiveness of countermeasures, we don't have that level of sophistication yet. I think that the industry is moving in that direction. We're seeing higher focus on metric tracking and really databases that are starting to be built. But for now, quantitative analysis is still difficult on the cybersecurity side. And so when we think about what impacts the likelihood of these threat agents attackers being successful, we really need to look at a different set of variables than on the safety side. And so for a successful attack, we can think about that likelihood being a result of the different types of threats, whether they are internal to the organization, thinking about a disgruntled employee or some sort of internal mistake, or also external, whether it is a nation state level attacker who has sophisticated resources, or a more general attacker who has access to now some of these hacking tools that are readily available. We also want to think about the vulnerabilities or the holes in our security position, whether they are in the software of the system, the hardware of the system, or how we're really using that. There exist exploits, things that attackers can really leverage to gain a foothold in the system. And then the last factor that affects this likelihood would be the target attractiveness. So thinking about what sort of political, economic, or personal drivers would really lead an attacker to go out and target a specific system. And so when we think about the possibility of a cyber attack and what this now does to our traditional safety scenario of looking at that overpressure, if an attacker is able to gain access and begin spoofing process values, not only are they going to be able to initiate a failure of the pressure control, but they can actually disable the alarms and prevent the operators from responding. Next, if we think about a sophisticated attack that also compromises the safety instrumented system, now that's another protection layer that would be affected. And so now we're really seeing that the likelihood of this event occurring has now jumped from 1 times 10 to the minus 6 to 1 times 10 to the minus 3. So essentially, by considering the impact of a cybersecurity attack of being that common cause failure, the risk is now 1,000 times greater than it was before. And so really this is a fundamental shift in how risk is looked at for these scenarios. And so although we do still have our pressure relief valve in this case, if we think to a scenario such as a runaway reaction or an excessive temperature scenario, when we don't have a physical protection, the risk may actually look even worse considering the common cause of cybersecurity. We'll have fewer protection layers that still remain, and could see really very high probability of this dangerous scenario occurring. If we look at this attack in detail and really think about how one attack can compromise multiple protection layers, we want to think about once the attacker gets onto the network, what devices are they able to connect to? What devices can they compromise? So if they are able to modify settings on the operator workstation, we can lose our alarm protection layer. We think about compromising the basic process control system either by the engineering workstation or for the controllers directly, they now have the ability to cause a failure of that system, to trigger our initiating event. And then, as we're often seeing safety systems connected on the same flat network, once they move over to the safety system, they're able to bypass and avoid that safety system as well. And so with that, we're really seeing cybersecurity pose a challenge to traditional process safety. We have a new, really high severity source of common cause failure that is going to bypass multiple protection layers at the same time. And because of this common cause, because of this new source of risk, we really have the potential for risk much higher than what we expect, and really a high priority of unmitigated risk that's not being evaluated with the traditional methods. We're also seeing challenges to traditional models in that cybersecurity risk can be harder to quantify, and really model in a linear sense what is going to happen once the attacker makes an intrusion to the network. And so it's going to take maybe some new types of thought, some tweaks to our existing models to really understand the cybersecurity impact. We're also seeing that the cybersecurity standards are certainly developing and adoption is improving, but process safety has really been something that has been a focus for the last 30 years. And in terms of cybersecurity management, we're talking at most really the last 10 years this has come into focus. And so many organizations don't have the same level of maturity for their cybersecurity management as they do for process safety. And so when we look at this, we don't want this to sound like it's all doom and gloom. Process safety has made really great strides over the years. We're really seeing cybersecurity adoption to pick up and for the maturity to grow there as well. And so when we understand the potential for risk, we also want to understand that there are actionable steps that can be taken that will help to significantly reduce this risk and really make sure that from both a safety and cyber perspective, that we are staying within our tolerable risk, that we are avoiding a high potential of these negative scenarios. And so when we think of what can be done to improve cybersecurity, there are a couple of very actionable things. It starts with training and awareness. This is always the first step in really reducing the likelihood of introducing an attack through some sort of unconscious error. We can look at physical and personnel security. These are areas where we really can implement relatively basic controls that are going to have a major impact. We also want to think about risk assessment and understanding what is our current cybersecurity exposure, what is our current risk, and then use that to help define our network segmentation strategy and our approach to defend in depth. And then lastly, we'll think about how can we integrate cybersecurity and process safety to really improve the management of both of them. On the training and awareness front, we really want to focus on and think about what our cybersecurity goals are for the organization and really establish that culture of adhering to best practices for cybersecurity. Making sure that our personnel are trained, that they understand good cybersecurity hygiene and are doing simple things that are going to lower the risk for the overall organization. We'll look at physical security and personnel security and really raising awareness there as well. And then thinking about, for risk assessment, how can we assess our cybersecurity readiness? And so really for the training and awareness, it all comes down to culture. And so if we think about for process safety, how really having that company culture of safety and implementing that process safety management was one of the first steps in really reducing the likelihood of these accidents. We're going to see that same level of commitment is really needed for cybersecurity to help reduce the likelihood of a successful attack. If we focus in on and look at our physical and personnel security, It's really for the physical security, a lot of times it's basic stuff. It's making sure that we have our perimeter security in place at the edge of the facility, thinking about for those rooms that have, our critical servers, our controllers, also looking at having them either be locked or manned 24/7, thinking about for equipment that's out in the field, are we able to put it in locked cabinets? Really to just make sure that just because someone has in-person access to the plant doesn't mean that they should have in-person access to the control system. Traditional measures such as security guards or video cameras and intrusion alarms can all be helpful and really play a role in locking down physical security as well. For personnel security, we can think about measures both to protect against internal attacks, so going through background checks and identity verification, as well as really limiting the amount of access and the number of accounts to the system. So we can follow the principle of least privilege, which essentially says we want to give users the minimum level of access that they need. And so limiting the engineers with administrative credentials, limiting the number of people who are able to log on and make changes to the system, that will help to reduce our exposure and limit the number of accounts that can be compromised. And then if we think about remote access, as we talked about now, 70% of control systems require some type. This is really something where we need to dive in and make it as secure as possible, whether it's through multi-factor authentication or really following industry best practice and implementing better secures for our remote access to the control system. The next step is to really know your cybersecurity risk. And so one way of looking at this is to think about the attack surface, or basically the vulnerabilities that are reachable and exploitable by attackers or threat agents. And so for all of those areas that we've talked about, if we think about our control system network, the actual physical devices and applications running on the system, as well as the people with access and the potential for them to be exploited through social engineering. Really having an effective cybersecurity risk assessment needs to look at all of these areas of exposure to really quantify what are the weak points in our defenses and what will attackers leverage to gain access to the system. And so understanding our different types of risks, understanding the practical steps that we can take to reduce these types of risks will really give us a better understanding of our current network security and what further actions are needed. And so as part of that risk assessment, we'll often look at segmenting the network. And so implementing firewalls to really prevent communication from the business network through to the automation and control system. And so by having better network segmentation, we can make it more difficult for attackers to gain access to the network and begin compromising those safety critical systems. For the risk assessment, we can also really outline our defense in depth because cybersecurity depends on how many different layers of protection we can have, much like functional safety or process safety, where we want to have different layers that reduce the likelihood of the attack being successful. And so starting with awareness, physical security, personal security, we can move to network segmentation and then look at what sort of system hardening or improve vulnerability scanning or patching can we do to really improve our system and add more layers that have to be compromised, that have to be bypassed in order for the threat to get to the control system. And so although cybersecurity represents an increased likelihood for common cause failure, by looking at the level of difficulty of the attack, by putting more barriers in place, we can make it less likely that an attack will be successful. The last thing that we can think about in terms of improving our approach to cybersecurity and process safety is really integrating them together and making sure that we don't need to start from the ground up for cybersecurity. we have existing risk management systems in these organizations. And so really leveraging them where possible can help us jumpstart it and get to improved results. So looking at our corporate risk criteria, leveraging those same benchmarks of saying what is a tolerable versus intolerable risk, and having this consistent risk matrix really allows us to compare what is our current safety risk and what is our current cyber risk, to prioritize what are the first steps that need to be taken. We can also really reference our cybersecurity management system in our process safety management. So we can lean on what's already in place there, lean on those quality systems and really leverage those to point to and really drive us to adopting cybersecurity management, which is critical for defining that culture and establishing really the actions that need to be taken. And then lastly, when we get to our lifecycle activities, we can coordinate between cybersecurity and process safety. So when we're conducting our traditional process hazard analysis, we can also now leverage those hazards as an input to really get a robust cyber risk assessment completed. And so have communication between those two core teams. We can also think about for our periodic audits or our functional safety assessments. And so a common one of those in the process safety world would be the pre-startup safety review, that independent check that before we start the system up, that all of the necessary activities have been completed and that we have adequate protections. And so by aligning that with cyber assessments, we're not only able to complete the activities more efficiently, but we get a better overall understanding of our risk and our current protections. And so by taking these steps, we really are able to significantly improve and really prepare to respond to cybersecurity threats. And so by going through and looking at what we covered today, we started with our landscape for process safety and cybersecurity, understanding how they've evolved over time and where they are today. We've looked at how cybersecurity really does offer new challenges to traditional protection layers and traditional process safety methods. But we've also looked at what are the actionable steps that we can take to help mitigate the cyber risk and really incorporate it into our process safety approach so that we are fully mitigating not just our safety, but also our cybersecurity risks as well. And so now I'm going to jump through just a couple of slides on our upcoming training courses. So if you do have questions that you didn't have a chance to ask yet during the presentation, please ask them now and we'll have 10 minutes to go through them at the end. So to support continued training during this period, we've really moved to and led a lot of online live training courses, both in cybersecurity, functional safety, and alarm management. Next week, later in the week, we will be teaching a CS 101 course. So if you're interested in learning more about cybersecurity and really want to just get started, this course is a really great way to do that. Also, the week of December 7th, I will be teaching our CS 102 course, which really dives into the cybersecurity lifecycle and helps to give a better idea of what are those cybersecurity strategies for reducing our risk. If you look through the course schedule and none of the dates work for you, we do also have online self-paced training that can be taken fully on your time, on your schedule. And so this is another great way to get access to those courses. As always, if you are interested in learning more about exida, catching upcoming webinars, and the other blogs and white papers that we publish, don't hesitate to follow us on all of the social media. And then lastly, if you do have a question that you aren't able to ask or have answered during this session, my email is pobrien@exida.com. And so don't hesitate to send me an email with any questions. Okay. So the first question we have is ISA 99 still relevant or superseded by IEC 62443? So ISA 99 has been modified and is actually now aligned with 62443 and is now called ISA 62443, I believe. So essentially, they're really working on the same thing, but IEC/ISA 62443 is the current version to look at. I forget if ISA is still calling the working group on it 99 or if they've updated the name. But really, ISA 99 and 62443 are very much aligned. Um, okay, so this is a question going back to the Triton attack. Um, is looking at what does it mean when we say they overcame a physical protection in order to create the attack. And so the specific protection layer here was actually a configuration switch on the controller where you could set it to either configuration or run mode. And when the switch was set to run mode, it was supposed to be impossible to update and make changes to the configuration. So that was, say, a physical layer to reduce the likelihood of cyber attack. But what happened was the safety system, the control system actually had been tied to the DMZ. And so once attackers established remote access to the demilitarized zone, they are able to leverage exploits to actually update the configuration and modify the controller while it was in run mode. So that was the um, uh, really the step in overcoming that physical protection layer. So the next question is, why not keep the safety instrumented system isolated from network access to outside traffic or agencies? And so certainly having better segmentation, having as much separation as possible between the safety system and the control system is going to improve our security and make it less likely that they'll both be compromised. But what we can see is having a true 100% air gap um, is not feasible to achieve for a number of reasons. The first is that the safety system does still need to be configured periodically, it does need to be updated. And so as soon as we connect to that engineering workstation, there's the potential that there are going to be cybersecurity vulnerabilities or a malware or some sort of attack on that system that can then gain access to the safety system. So there are certainly things that we can do to reduce the likelihood of the SIS being compromised, but we're not going to be able to fully mitigate that potential. There still exists the possibility for it to be compromised. This next question is, can we assume that cybersecurity risks can be implemented as part of the common cause failure analysis? Um, and so it definitely, it would be a good concept of thinking about how can we, leverage common cause failure that's already looked at and use this to, account for cybersecurity risk. Now, where that is difficult in the traditional LOPA sense is that really we are assuming full independence between those different protection layers, between the controller, the alarm layer, and the safety layer. Typically in that LOPA analysis, we assume that they're fully independent. We could add in, say, a common cause factor for cybersecurity, but we would need to really have a better understanding of the likelihood of the attack and a number of the different factors that can impact it. So I think part of it is starting to account for cybersecurity and common cause failure, but there are really some other analysis steps that have to be done as well. Um, okay. This next question is talking about avoiding providing a soft bypass for the safety systems to reduce the risk. So that is something that could help reduce the risk to the safety systems, but from an operability standpoint, it's unlikely that many operating facilities could fully go to that standpoint. And again, while it would reduce the risk, we can't fully eliminate it. So the next question is going back to our LOPA example, where we look at the cyber attack. And so the question here is that moving from the traditional LOPA to the cybersecurity analysis, we kept the initiating event likelihood as 0.1. And so if that likelihood changed, would the residual risk move and maybe not be 1,000? So say the probability of a cyber attack is only 1 in 100 years, then our residual risk would be 100 instead of 1,000. And so from a math perspective, absolutely that changing the likelihood of our initial cybersecurity attack is going to impact our residual risk. In terms of really honing in on and thinking about what is the correct likelihood of a targeted attack, it depends on the level of skill required. For general attacks, we often consider a likelihood of multiple times a year to at least once per year. Typically for a targeted attack of maybe some skill, but not, say a nation state attack, we might look at 0.1. And then when we get into more of a nation state attack, that's when a lot of times we'll look at a risk of 0.01. And so it is possible that for that scenario, maybe 0.01 would be a better initiating likelihood. The key takeaway though is whether the residual risk is 100 to 1,000 times more than what we would have previously guessed. This is really now a significant driver of that risk. Okay, the next question here is, what is the necessary requirement for something to be an instrumented protection layer or an independent protection layer in cybersecurity? And so we follow similar guidelines to the LOPA. We think about how is it managed, what sort of metrics and audits do we have on it? Do we know if that protection layer has failed? And then really thinking about the independent requirement is where it becomes even trickier on the cyber side. And so there are a couple of different models for attack where we can try to understand what are, say, the independent stages, and making sure that we are looking at maybe a protection for each stage instead of giving credit for maybe operator training as well as operator response, where those are both heavily dependent on the user and likely aren't independent. So I think we've got a question here about really the impact of risk on process control systems at each of the different layers of protection. And so the key takeaway here is that for any automated system, any control-based system or protection layer based off of a connected system, there is a potential for an attacker to gain access and really disable that protection layer or cause a hazardous scenario. And so, certainly, if there are more questions on that, we can maybe go into detail more on how that attack might be executed on a separate webinar. But we do have a couple webinars on, say, detailed risk assessment where we dive on that a little bit more in depth. All right, so we do still have quite a few questions left that I haven't gotten time to. So what I will say, for those who are able to hang on, I'll keep going through a few more of the questions, but we will also email out a Q&A sheet that will have the full list of questions and answers for all of the attendees. So for those of you who have to hop off, thank you very much for joining us today. I hope you found the information to be helpful and useful, and I really look forward to kind of continuing discussions on this topic and understanding how we can make improvements both in process safety and cybersecurity. Okay, so let's see the next question. Okay, so there are a couple questions about, are the webinars recorded? And so yes, this webinar will be posted to YouTube and can be rewatched and reviewed there as well. So this question about the cyber attack being a common cause failure, thinking about how does it enter into the equation of the SIL calculation. So I think what we've seen is that it's difficult to quantify in the really the SIL level, especially because the safety system can be compromised by the attack as well. So whether we have a SIL 2 system or a SIL 3 system, if the attackers gain access, it's really not going to give us any additional protection. And so it's more important to look at really what can be done to prevent the attacker from getting access to that safety system to help reduce the likelihood from the cyber standpoint. This next question, in which steps of the SIS lifecycle should cybersecurity be implemented? Really, there are a lot of parallels at kind of each of the steps in the analysis, implementation, and design phase. And so there's a technical report, ISA TR 84.00.09, that really looks like how the overall safety lifecycle and overall cybersecurity lifecycle can really be tackled together, and has kind of those key integration points. So what I would say is, on the analysis side, we do want to coordinate our risk assessments, and there are a number of other opportunities to do so as well, such as doing our cybersecurity testing at the same time that we're doing our cyber FAT, and again, repeating that at the site acceptance test. There is one question about conducting penetration testing on the industrial control system. So what I would say for that is really we never want to do penetration testing on a live industrial control system. The reason being it's physically connected and it can have unintended consequences such as very likely downtime or even losing safety layers and really increasing that risk. So typically we would only look at penetration testing more at the factory acceptance test level or in a place where we can 100% guarantee that there's going to be no impact on the live system. But yes, penetration testing is something that we have some experience with, and there are ways to do it, but again, making sure it's not on a live system. All right, so thank you very much for all of the questions. I'm sure there may have been one or two that I missed going through the list, so I will make sure that I capture those when we send out the Q&A. But thank you very much for your time on the webinar, and please enjoy the rest of your day. Thanks.